Welcome! In this session, we'll tackle the problem titled Maximum Points in an Archery Competition. This problem challenges us to strategically allocate resources in order to maximize a score under given constraints. Let's dive into the details and explore possible solutions. In this problem, we have an archery competition between Alice and Bob, which consists of 12 rounds. Each round awards points based on how well the participants perform. Alice, the reigning champion, has already scored some points in the competition. Bob, on the other hand, wants to beat Alice's score by achieving the maximum possible points. To do this, Bob has a limited number of arrows, represented by the variable number arrows, which he can distribute across the 12 rounds. For each round, Alice has already used a specific number of arrows, given in the array Alice arrows. In order to win the points for a particular round, Bob must use more arrows than Alice did in that round. However, if Bob uses the same number of arrows as Alice or fewer, he does not earn any points for that round. If Bob wins a round, the points he earns are equal to the index of that round. The goal is to determine how Bob should distribute his arrows across the rounds to maximize his score, while ensuring he uses all of his arrows. To solve this problem, the output format requires us to return a list of 12 integers, where each integer represents the number of arrows Bob uses in the corresponding round. The total number of arrows used across all rounds must exactly equal number arrows. Let's consider an example to make this clearer. Suppose Bob has 9 arrows, and the array Alice arrows is given as 1, 1, 3, 2, 4, 0, 0, 0, 0, 0, 0, 0. Here, Alice has already used arrows in the first few rounds, and Bob needs to plan his distribution carefully. One possible output could be 0, 2, 4, 3, 0, 0, 0, 0, 0, 0, 0, 0. This output indicates how Bob distributes his arrows across the 12 rounds. Let's break down the reasoning behind this output. In round 1, Alice used 1 arrow, so Bob uses 2 arrows, earning him 1 point. In round 2, Alice used 3 arrows, so Bob uses 4 arrows, earning him 2 more points. In round 3, Alice used 2 arrows, so Bob uses 3 arrows, earning him 3 points. Adding these up, Bob's total score is 1 plus 2 plus 3 is equal to 6. Notice that the total number of arrows Bob used is 2 plus 4 plus 3 is equal to 9, which is exactly equal to number arrows. This ensures we meet the problem's constraints while maximizing Bob's score in this scenario. Now, let's look at another example. Suppose Bob has only 3 arrows, and Alice arrows is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. In this case, Alice has not used any arrows in any round. One valid output could be 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Here, Bob distributes his 3 arrows across the first 3 rounds. In round 0, Bob uses 1 arrow and earns 0 points. In round 1, Bob uses 1 arrow and earns 1 point. In round 2, Bob uses 1 arrow and earns 2 points. This gives Bob a total score of 0 plus 1 plus 2 is equal to 3, and he uses all 3 of his arrows as required. The problem also highlights edge cases, such as when Bob has the minimum or maximum number of arrows, or when Alice's scores are extremely low or high. These scenarios test the flexibility of Bob's strategy in distributing his arrows to achieve the maximum score possible. In this problem, our goal is to distribute a fixed number of arrows between Bob and Alice in a way that maximizes Bob's score. To start, let's look at a brute force approach. Here, we consider every possible way to distribute the arrows across the 12 rounds, calculating Bob's score for each configuration. Bob earns points for a round only if he uses more arrows than Alice in that round. While this method ensures we find the optimal solution, the number of combinations grows exponentially with the number of arrows, resulting in a search space of size O, number arrows plus 1, 12. This makes brute force computationally infeasible for larger inputs. To improve on this, we could consider backtracking with pruning, where we explore the decision tree of arrow distributions but eliminate branches that exceed the number of arrows or cannot lead to a higher score than the current maximum. While pruning helps reduce the computational load, the search space is still exponential, so this method remains impractical for large values of number arrows. Even with pruning, the backtracking approach struggles with scalability due to its exponential complexity in the worst case. This brings us to a more structured solution: dynamic programming. By leveraging a DP table, we can systematically determine the optimal arrow distribution. The intuition here is to define states that represent the maximum score Bob can achieve with a specific number of arrows distributed across a certain number of rounds. The key insights are that Bob earns points for a round only if he uses more arrows than Alice in that round, and his total score is the sum of points from such rounds. By breaking the problem into smaller overlapping subproblems and solving them iteratively, we can avoid redundant computations. This structured approach allows us to address the problem more efficiently than the earlier methods while still guaranteeing an optimal solution. To implement the dynamic programming approach, we define dp(i)j as the maximum score Bob can achieve with j arrows distributed across the first I rounds. For each round, Bob has two choices: skip it or compete. If Bob skips the round, the value of dp(i)j remains the same as dp(i1j), which represents the score without considering the current round. If Bob competes, he needs to allocate more arrows than Alice used in that round, which requires j Alice arrows, I. In this case, the new value becomes dp(i)j equals dp(i1j Alice arrows, I1 plus points, I, where points is the score for that round. The base case is straightforward: if no rounds are considered, the score is 0. At the end, the value at dp(12) number arrows gives the maximum score Bob can achieve. The complexity of this approach is 12* number arrows, since the DP table has dimensions of 12 rounds by number arrows, making it efficient for the problem's constraints. We selected the dynamic programming approach because it strikes the best balance between efficiency and optimality. Unlike brute force or backtracking, DP avoids redundant computations by breaking the problem into smaller overlapping subproblems. The breakthrough here was recognizing the problem as a variation of the knapsack problem, where each round represents an item, the arrows correspond to weight, and the points are the value. This insight allowed us to tailor the DP transitions to ensure that Bob's distribution of arrows is optimal and adheres to the rules of the competition. Additionally, the DP table structure enables us to reconstruct the specific arrow distribution, providing a complete solution. While this method is well suited for the given constraints, it may require further optimizations like space compression if number arrows were significantly larger, such as exceeding 10 to the power of 5. However, within the parameters of this problem, dynamic programming offers the most efficient and accurate solution. In this problem, we need to strategically distribute a limited number of arrows between 12 rounds of an archery competition. Bob is competing against Alice, and in each round, Alice has already used a specific number of arrows. Bob can only win a round if he uses more arrows than Alice in that round. Each round has an associated score, and Bob's goal is to maximize his total score while staying within the limit of arrows provided. To solve this, we first need to understand the inputs and constraints. We're given the total number of arrows Bob can use and an array representing the arrows Alice used in each round. The output we're looking for is an array showing how Bob should distribute his arrows to maximize his score. The brute force approach to solve this problem involves exploring all possible ways Bob can distribute his arrows. For each distribution, we calculate Bob's score based on the rounds he wins and track the distribution that results in the highest score. To implement the brute force approach, we start by generating all possible distributions of arrows using a technique called bit masking. Each subset of rounds corresponds to a possible combination of rounds Bob could attempt to win. For a given subset, the number of arrows Bob needs to win a round is one more than the number Alice used in that round. For each subset, we calculate the total number of arrows required. If this total exceeds the limit of arrows Bob has, we discard that subset. If the subset is feasible, we compute Bob's score by summing up the scores of the rounds he wins. We keep track of the distribution of arrows and the corresponding score to ensure we retain the best result. Additionally, once the arrows are distributed to win specific rounds, any remaining arrows can be assigned arbitrarily to one of the rounds Bob competed in, ensuring no arrows are wasted. Finally, we return the distribution that achieves the maximum score. The use of bit masking here is key because it allows us to efficiently generate all possible subsets of rounds Bob can compete in. Each subset corresponds to a unique combination of rounds, represented as a binary number where each bit indicates whether Bob competes in the corresponding round. This approach also allows for early pruning. If the arrows required for a subset exceed the available arrows, we can skip that subset entirely. While exploring all subsets guarantees an optimal solution, it can be computationally expensive. Greedy alternatives, such as prioritizing rounds with higher scores first, might provide faster approximations in practice. For data structures, we use an integer for bit masking, arrays to store Alice's arrows and Bob's current distribution, and variables like max_score to track the best score so far. The time complexity of this approach is 2 to the power of n*n, where n is the number of rounds, as we generate all subsets and evaluate each in n. The space complexity is n, primarily for storing intermediate results. To translate the concept into code, we start by iterating over all subsets using bit masking. Each subset is represented as an integer, and we use bitwise operations to check which rounds are included. For each round in the subset, we calculate the arrows Bob would need to win that round, which is one more than Alice used. If the total arrows required exceeds Bob's limit, we stop evaluating that subset. Otherwise, we update the arrows used, the score for the current subset, and the distribution of arrows. Once all rounds in the subset are processed, we check if the current score is better than the maximum score recorded so far. If it is, we update the max_score and store the current distribution as the best distribution. This ensures that by the end of the loop, we have the optimal distribution of arrows that maximizes Bob's score, given the constraints. After determining the best distribution, we handle any remaining arrows. These leftover arrows can be assigned to any round where Bob already competed. For simplicity, we add them to the first round in the best distribution where Bob used arrows. This ensures that all arrows are accounted for and no resources are wasted. The final distribution is then returned. There are a few edge cases to consider. If Bob has fewer arrows than required to win any round, he cannot win any round, and the output should be an array of zeros. If the total arrows match the exact requirements to win certain rounds, ensure no arrows are wasted. Additionally, if multiple distributions yield the same maximum score, any valid distribution can be returned. Optimizing this process further could involve dynamic programming or other heuristics to reduce computational complexity while maintaining accuracy. To improve the brute force approach, we can incorporate optimizations like pruning subsets early if the required arrows exceed the limit. Another optimization is to process rounds in descending order of their scores, prioritizing high-value rounds first. Sorting the rounds by their score-to-arrows ratio ensures that Bob gets the most points for his arrows in a greedy manner. While the brute force method guarantees an optimal solution, it can be computationally expensive due to the exponential number of subsets. Depending on the constraints, alternative methods like dynamic programming or greedy heuristics might strike a balance between efficiency and accuracy. These optimizations can significantly reduce the computational overhead while still achieving near-optimal results, making the solution more scalable for larger problem sizes. Here, we start by defining the maximum Bob points method inside the solution class. This method takes two inputs, number arrows, which represents the total number of arrows Bob has, and Alice arrows, which is a list showing how many arrows Alice used in each of the 12 rounds. The goal is to calculate the maximum points Bob can earn by strategically distributing his arrows across the rounds. We initialize two variables, max_points to track the highest score Bob can achieve, and best_distribution, which is a list of 12 zeros, to store the optimal allocation of arrows for Bob. Next, we use a loop to iterate over all possible subsets of rounds that Bob could win. Since there are 12 rounds, there are 2^12 or 4096 possible combinations, and we represent each combination using a binary mask. For each mask, we calculate the total arrows Bob would use, the points he would earn, and the distribution of arrows for that combination. This is done by checking each round individually. If the current round is included in the mask, Bob needs to use one more arrow than Alice did in that round to win it, and he earns points equal to the round number. We also update Bob_distribution to reflect this allocation. After calculating these values, we check if Bob's chosen strategy is valid by ensuring that the total arrows used do not exceed number arrows. If the strategy is valid and yields a higher score than the current max_points, we update max_points and set best_distribution to the current allocation. This ensures we store the best possible outcome as we evaluate all combinations. Once we have identified the best strategy and its corresponding arrow distribution, we calculate how many arrows are still in use by subtracting the total arrows in best_distribution from number arrows. These remaining arrows can be added to any round to maximize their usage. In this implementation, we simply allocate the extra arrows to the first round that allows for it, ensuring that the total number of arrows used equals number arrows. This is done by iterating over the rounds and adding the remaining arrows to the first available round before breaking out of the loop. Finally, the method returns best_distribution, which represents the optimal way for Bob to distribute his arrows across the 12 rounds to achieve the maximum possible score while staying within the given constraints. This approach ensures that every combination is analyzed, and the best possible outcome is chosen efficiently within the given limits. Here, we are implementing a solution to maximize Bob's points in the archery competition. The method maximum Bob points takes the total number of arrows Bob can use and an array representing the arrows Alice used in each round. We start by initializing variables to track the maximum points Bob can achieve and the best distribution of arrows across the 12 rounds. To explore all possible strategies, we use a bitmask approach to iterate over all subsets of rounds Bob could potentially win. Since there are 12 rounds, we have 2 to the power of 12 combinations. For each subset, represented by mask, we determine the arrows required and the points Bob would earn if he chooses to win the rounds indicated by the mask. If Bob decides to win a particular round, he needs to use one more arrow than Alice did for that round. This is tracked by incrementing arrows used and updating Bob points accordingly. The distribution of arrows for the current strategy is stored in the Bob distribution array. Finally, if the total arrows used under the current strategy do not exceed the allowed limit and the points are higher than the best we've seen so far, we update our maximum points and the best distribution to reflect this strategy. Once we have determined the best strategy for Bob, we need to handle any remaining arrows that were not used. To ensure all arrows are allocated, we calculate the difference between the total arrows Bob is allowed to use and the sum of arrows in the current best distribution. These remaining arrows are then added to any round, which, for simplicity, we do by iterating through the rounds and adding the remaining arrows to the first available round. This ensures all arrows are utilized without violating the competition rules. Finally, the method returns the array best distribution, which represents how Bob should distribute his arrows across the 12 rounds to maximize his points while staying within the limit of arrows he can use. This completes the implementation of our solution. To solve this problem, we start by initializing 2 variables, max_points to 0, which will track the maximum points Bob can achieve, and best_distribution to an array of 12 zeros, representing Bob's distribution of arrows across the rounds. The key idea here is to iterate through all possible subsets of rounds that Bob could win, represented by mask, which ranges from 0 to 2 to the power of 12 1, or 4095 in decimal. Each bit in the mask indicates whether Bob is attempting to win a specific round. For instance, when mask equals 3, its binary representation is 000000000011, meaning Bob is targeting rounds 0 and 1. In this scenario, the arrows required are calculated as Alice's arrows in those rounds plus 1 extra arrow for each round. For mask equals 3, the total arrows used are 4, which is valid since it does not exceed the total number arrows of 5. Bob scores 1 point, and his distribution becomes 2, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Therefore, we update max_points to 1 and save this distribution as the current best. On the other hand, for mask equals 7, representing rounds 0, 1, and 2, the arrows used exceed the limit, so this configuration is invalid. The process continues, evaluating all other masks in the range. Once all possible masks have been evaluated, we allocate any remaining arrows to Bob's distribution. In this example, Bob used 4 arrows, leaving 1 arrow unused. We can assign this remaining arrow to any round, such as round 0, which adjusts Bob's distribution to 3, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Finally, the output for this example is 3, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now, let's explore a more complex scenario with a larger input, where number arrows is 9, and Alice's distribution is 0, 2, 4, 1, 3, 0, 0, 0, 0, 0, 0, 0. In this case, we follow the same process to maximize Bob's points by iterating through all masks. We start with the same initialization, max underscore points is set to 0, and best underscore distribution is an array of 12 zeros. For mask equals 14, which corresponds to the binary representation 000000001110, Bob attempts to win rounds 1, 2, and 3. The arrows required are calculated as Alice's arrows in these rounds plus 1 extra for each, totaling 10 arrows. Since this exceeds the available number arrows of 9, this configuration is invalid. However, for mask equals 11, which is 000000001011 in binary, Bob targets rounds 0, 1, and 3. Here, the arrows used are 6, which is valid, and Bob scores a total of 4 points. The corresponding distribution for Bob becomes 1, 3, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. We update max underscore points to 4 and save this as the best distribution. After evaluating all masks, Bob has 3 remaining arrows, which can be allocated to any round, such as round 0, resulting in a final distribution of 4, 3, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. The output for this example is 4, 3, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. Now, consider an edge case where number arrows is just 1, and Alice's distribution across all rounds is 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Here, Bob has very limited resources, and we follow the same process of iterating through all masks, from 0 to 4095. For every mask, the total arrows required to win even a single round exceed the available 1 arrow. As a result, Bob cannot win any round in this scenario. However, instead of leaving the distribution empty, we allocate Bob's 1 arrow to any round, such as round 0, resulting in the final distribution 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The output for this edge case is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. In this problem, we are leveraging a bitmask approach to iterate over all possible subsets of rounds Bob could win. Since there are 12 rounds, the total number of subsets is 2 raised to the power of 12, which equals 4096. For each subset, we examine all 12 bits of the bitmask to determine which rounds Bob wins. This process takes 12 time per subset. Once we identify a valid subset, meaning the total arrows used do not exceed Bob's available arrows, we compare the resulting score against the current maximum score. If the new score is better, we update the best arrow distribution. These comparison and update steps are constant time operations, 1. Overall, the time complexity for iterating through all subsets is 2 to the power of 12 * 12, which simplifies to 2 to the power of 12, since the factor of 12 is considered negligible. At the end, when distributing any remaining arrows, we perform one final pass through the 12 rounds, which contributes 12 or 1 to the complexity. Therefore, the dominant term is 2 to the power of 12, making it the overall time complexity of the algorithm. Now let's look at the space complexity. The algorithm only uses a constant number of variables, such as max underscore points and arrows underscore used, which require 1 space. Additionally, we maintain an array, best underscore distribution, of size 12 to store the optimal allocation of arrows. This array requires 12 space, which simplifies to 1 in big O terms. For each subset during the iteration, a temporary array, Bob underscore distribution, is used to track the current allocation of arrows. However, since this array is recreated for each subset and does not persist outside the loop, it also contributes 12 or 1 space. Importantly, the algorithm does not rely on any recursive calls or additional data structures that would increase memory consumption. As a result, the overall space complexity remains constant at 1. Comparing this optimized approach with a brute force method highlights its efficiency. A naive approach would involve generating all possible ways to distribute Bob's arrows across the 12 rounds. This is a combinatorial problem, where the number of distributions corresponds to solving the equation x_1 plus x_2 plus x_12 equals number arrows for non-negative integers. Using the stars and bars formula, the number of solutions is c, number arrows plus 12 to 1, 12 to 1, which grows exponentially as number arrows increases. In contrast, the bit mask optimization simplifies the problem by focusing only on subsets of rounds Bob could win, reducing the time complexity to 2 to the power of 12. This is significantly more efficient given the fixed number of 12 rounds. Furthermore, the time complexity remains 2 to the power of 12 in the best, average, and worst cases because the algorithm evaluates all subsets regardless of the input. Similarly, the space complexity remains consistently 1 in all scenarios, making this approach both time and space efficient. To mathematically prove the algorithm's time complexity, we start by noting that the total number of subsets is 2 to the power of 12, or 4096. For each subset, we perform operations that take 12 time, such as examining the bitmask and determining the score. Thus, the total time required is 2 to the power of 12*12, which simplifies to 2 to the power of 12, since constants are ignored in big O notation. On the space side, the algorithm uses a constant amount of memory for variables and two arrays of size 12, both of which contribute 1 space. No additional structures or recursive calls increase memory usage. Therefore, the algorithm achieves a time complexity of 2 to the power of 12 and a space complexity of 1, making it optimal for the given constraints. When tackling this problem, there are several common pitfalls to watch out for. First, when using a brute force approach, it's easy to miss some valid distributions of arrows, which can lead to suboptimal solutions. For instance, you need to ensure you're considering edge cases like allocating all the arrows to a single player. Next, tie-breaking scenarios are another area where mistakes often occur. If Alice and Bob end up with the same number of arrows in a round, the problem may specify a rule for the tie, such as Bob winning ties. Ignoring this detail can lead to incorrect scores. Another issue is mismanaging the arrow budget. Some solutions allocate arrows without ensuring the total stays within the given limit, which results in invalid distributions. Lastly, when implementing recursive or dynamic programming solutions, overcomplicating the state design is a frequent error. Adding unnecessary states or dimensions to your DP table can make the implementation overly complex and harder to debug. Focus on the essential states, like the remaining arrows and the scores, to keep things simple and efficient. To handle this problem effectively, it's important to account for edge cases. For example, consider scenarios where no arrows are available, or where Alice has 0 scores across all rounds. These edge cases can reveal weaknesses in your approach, so always test them to ensure robustness. From an interview perspective, this problem highlights several key patterns. It's a great example of optimization under constraints, which is common in both dynamic programming and backtracking problems. To solve efficiently, identify overlapping subproblems and use techniques like memoization or iterative DP. When explaining your solution, communicate your choice of states, transitions, and base cases clearly. This clarity is something interviewers value highly. Also, don't be afraid to start with a brute force or naive approach. Showing how you refine and optimize your solution step by step can demonstrate your problem-solving process. Finally, after implementing your solution, run it against edge cases and stress test it with large inputs to show its robustness and scalability. This problem shares similarities with several other optimization and resource distribution problems you might encounter on platforms like LeetCode. For instance, LeetCode 518, Coin Change 2, involves distributing coins to achieve a target sum, which is conceptually similar to distributing arrows. Another related problem is LeetCode 416, Partition equals Subset Sum, where you aim to divide resources to either maximize or balance scores. LeetCode 1049, Last Stone Wait 2, also focuses on optimization under constraints, specifically minimizing the difference between two groups. Lastly, LeetCode 474, Ones and Zeros, deals with balancing resources, in this case, ones and zeros, across multiple constraints. Familiarizing yourself with these problems can deepen your understanding of resource allocation and constraint optimization, which are core themes in the maximum points in an archery competition problem. There are multiple approaches you can take to solve this problem, each with its own advantages and trade-offs. Starting with brute force, this method is straightforward to implement and ensures that all possibilities are considered. However, it's computationally expensive, with an exponential time complexity, so it's only feasible for small inputs. A more efficient approach is dynamic programming, specifically using a knapsack-like strategy. This method reduces the time complexity significantly, often to n*m, where n is the number of rounds and m is the aero budget. Dynamic programming handles large inputs well, but it requires careful design of states and transitions, and debugging can be challenging. Another option is using a greedy heuristic. This approach is fast and easy to implement, making it practical for quick solutions. However, it doesn't always guarantee the optimal result, particularly in edge cases where earlier decisions impact the global optimum. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make between accuracy and efficiency. Great job! We've summarized the key aspects of the problem and discussed takeaways for tackling similar challenges. Keep practicing and applying these concepts to build your problem-solving skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!